You've been told Mars is our backup planet, our plan B, the place we'll escape to when Earth falls apart. But what if that belief is completely upside down? What if Mars isn't a new home at all, but a trap we've romanticized into a dream? In this video, we're going to walk straight into that dream, pull it apart piece by piece, and see what's really waiting for us on the red planet when the fantasy finally hits reality. But before we continue, please subscribe to the channel to give your support. Let's continue. Start with the simplest thing, temperature. On Mars, the average surface temperature is around minus 60 degrees Celsius. That's about minus 76 degrees Fahrenheit. That's not a cold winter, that is the baseline. At the poles, in winter, it can drop to around minus 125 Celsius, roughly minus 193 Fahrenheit. That is beyond anything you have felt outside on Earth. If your suit heat fails, you do not get frostbite over hours. You go into life-threatening hypothermia in minutes. And it gets worse when you look at how unstable that cold is. Near the equator, on a good day, the ground might briefly climb a little above 0 Celsius, 32 Fahrenheit. You hear that and think, okay, that's survivable, I can work with that. Then the sun sets, the thin air stops doing almost anything to hold heat, and the temperature can drop by tens of degrees in a single night. No oceans, no thick atmosphere, nothing to smooth those swings. Your habitat and your suit are doing all the work, all the time. So why is Mars like this? Why is a planet that looks so Earth-like in photos so hostile in reality? The answer starts with something that sounds harmless. Size. Mars is small. Its diameter is about 6,780 kilometers, around 4,212 miles. Earth is about 12,742 kilometers, around 7,918 miles. That means Mars has less mass, which means weaker gravity at the surface, about 3.71 meters per second squared, around 38% of Earth's gravity, about 0.38 g. Low gravity sounds cool when you think about jumping higher, but for the planet itself, it is a problem. A smaller world loses heat from its interior faster. Billions of years ago, Mars probably had a hot, active core like Earth, and that churning metal in Earth's core is what drives our global magnetic field. Mars cooled and slowed down sooner. Its internal dynamo mostly shut down, and the strong, planet-wide magnetic shield went away. Once that shield weakens, the sun stops playing nice. Charged particles in the solar wind slam into the upper atmosphere over and over. And with each hit, some atoms, some molecules, get enough energy to escape into space. It is a slow leak, but given hundreds of millions of years, it strips away a lot of gas. That means the thick atmosphere Mars might have had early on and the liquid water that may have existed on its surface did not last. The planet shifted toward thinner air, lower pressure, colder climate, and it had no way to reverse that on its own. So you might say, fine, the planet is smaller, the core is quiet, the magnetic field is gone, but there is still some atmosphere, right? Maybe we can just work with what is left. Here's where the picture gets brutal. The air on Mars today is not something your body can use, and it's barely even there. At the surface, the atmospheric pressure on Mars is about 600 pascals. That's roughly 0.6% of Earth's sea level pressure. If you want an intuition, that's like being around 35 kilometers up above Earth's surface, more than 20 miles, far above where commercial jets cruise. That is the kind of pressure you get standing on the ground on Mars. It is so low that without a pressurized suit or habitat, your blood and body fluids are not stable. Your lungs cannot meaningfully pull in oxygen. You cannot simply adapt to it. And the composition is all wrong. On Earth, the air is roughly 78% nitrogen, 21% oxygen with a little argon and carbon dioxide. On Mars, about 95% of the air is carbon dioxide. Around 2 to 3% is nitrogen. A bit over 1% is argon. Oxygen is only a trace. Your lungs do not care that there's some oxygen mixed in there. They need enough oxygen pressure to support your cells, and Mars just doesn't have it. It's effectively zero compared to what you need to stay conscious and alive. This is why it's misleading to look at a Mars landscape and think, we'll just wear a jacket and a helmet. You're not stepping out into a different kind of cold mountain. You're stepping into an environment that, in terms of pressure, is very close to a vacuum. The planet's surface has rock, dust, ice, but the gas layer on top is so thin and so different from Earth's that for a human, it might as well not exist. Now, here's the key misunderstanding that drives a lot of public optimism. People say we can live on Mars, as if that means Mars is a place where humans can actually live in any normal sense. But what they really mean is we can maybe keep a small group of people alive inside sealed systems if those systems work almost perfectly. That difference is huge and it matters. On Earth, the planet gives you margin for error. You can step outside in the wrong clothes, you can get caught in a storm, your heating system can fail, and in most places you still have time. You can breathe the air, you can find water, you can move, get help, improvise. You live inside a thick layer of atmosphere with the right pressure and oxygen level that constantly supports you without machines. On Mars, all of that is gone. Every second you're not inside a pressurized habitat or a working suit, you're dying. There is no breathable air, there's almost no pressure, the temperature wants to drop your body heat out into space. Your house is no longer a regular building, it's a life support shell with pumps, heaters, scrubbers, valves, sensors, all working together non-stop. If any core part fails at the wrong time, the planet does nothing to help you. It just finishes the job. So yes, in theory, we can put people there. We can land habitats, run reactors or huge solar farms, recycle air and water, and keep a small crew alive for months or years. But that's not the same thing as saying Mars is a place humans can truly live. It's not like moving to a harsher version of Earth. It's more like living full-time inside a research submarine, except the ocean outside is colder, thinner, and more deadly than any sea you've ever known. This is the core point for everything that comes next. Mars by itself doesn't give you what you need. Not air, not pressure, not temperature, not protection. Any human presence there is basically a bubble of Earth running on complex hardware glued to the surface of another planet. And that's before we even talk about what air actually has to do, how pressure really works on your body, and what happens when the numbers are wrong. Because once you look closely at the air alone, what it's made of, how dense it is, how much pressure it puts on your skin and inside your lungs, you realize something even sharper. It's not just that Mars doesn't have the right atmosphere, it's that your body literally cannot function in that environment without a machine around you every second of your life. And if you need a machine to survive every breath 24 hours a day, then we have to ask very seriously what it really means to live on that world at all. Take a breath right now, wherever you are. Feels automatic, right? You don't have to think about chemistry, you don't have to think about pressure, your body just runs on the air around you. On Mars, that one simple act, taking a breath, is impossible without a machine wrapped around your body every second of your life. On Earth, the air is mostly nitrogen, around 78%, about 21% oxygen, and a little argon and carbon dioxide. Your lungs are tuned to that mix, and more importantly, to the pressure it sits at. At sea level, the total pressure is about 101 kilopascals. Think of that as a measure of how hard the air is pushing on your skin and into your lungs. Out of that, roughly 21 kilopascals comes from oxygen. That oxygen pressure is what actually keeps you alive. It pushes oxygen molecules into your blood. Now look at Mars. The atmosphere there is about 95% carbon dioxide, around 2 to 3% nitrogen, roughly 1 to 2% argon, and only a trace of oxygen and water vapor. The total pressure at the surface is about 600 pascals. That's 0.6 kilopascals, less than 1% of Earth's sea level pressure. So even if Mars had the same percentage of oxygen as Earth, which it doesn't, the absolute oxygen pressure would still be far too low to support your brain and your organs. Here's the key idea. Your lungs don't care about percentages. They care about how much oxygen is actually pushing on them. On Earth, that push from oxygen is around 21 kilopascals. On Mars, the total push from all gases combined is about 0.6 kilopascals. So the push from oxygen, which is only a trace, is basically zero compared to what you need. If you open your helmet on Mars, you wouldn't get thin air. You would get almost no usable air at all. You would take a breath, nothing meaningful would go into your blood, and you would pass out in seconds. You might think, okay, but what if I just bring pure oxygen, like a fighter pilot or a high-altitude climber? Surely I could breathe if I pump enough oxygen into my mask. Here is the next problem. Even before you run out of oxygen, the environment itself starts to break your body. At very low pressures, something strange happens to water. At around 6 to 7,000 pascals, a level called the Armstrong limit, water can boil at normal human body temperature. You do not need heat, you just need low pressure. Mars sits around or below this range over much of its surface. That means if you step outside without a pressure suit, the water in your saliva, the moisture on your eyes, and the fluids near your skin start to form bubbles. They do not boil like a pot on a stove, but they begin to vaporize quickly. Your tissues swell, your lungs cannot work, and you lose consciousness in seconds. This is not science fiction. It is just a phase diagram of water applied to your body. Your blood is mostly contained and under internal pressure, so it doesn't instantly explode or something dramatic like that, but you're still in deep trouble. Air does not move into your lungs properly. Gases in your body expand, and you simply cannot stay alive. You die not because it is cold, not because of dust, but because the basic pressure around you is out of the range your body can handle at all. So you might say, fine, that just means we never go outside without a proper suit. We'll live inside pressurized habitats. We'll create our own little pockets of Earth conditions. How hard is it to make one room with normal air? Let's walk through that, because this is where you see how extreme the engineering really is. Imagine a modest living area, around 100 square meters of floor space. That is like a medium-sized apartment or a small house with a ceiling height of about 2.5 meters. That gives you a volume of about 250 cubic meters. To make that room feel somewhat like Earth, you want maybe 70 to 80 kilopascals of pressure inside, a bit under full Earth sea level. That pressure across that volume means you're holding tens of thousands of kilograms of air above the Martian ground. Around 20,000 kilograms is a reasonable ballpark. That is not just some air, that is the mass of several loaded trucks if you think in everyday terms. All of that gas has to be created, moved, and maintained. On Earth, you just open a window. The atmosphere does the rest. On Mars, you need industrial-scale systems. Compressors to squeeze the gases, storage tanks that don't leak, equipment to separate carbon dioxide from the tiny bit of nitrogen, systems to generate oxygen, either from ice or from carbon dioxide using power-hungry machines. And remember, Mars does not give you an easy supply of nitrogen or oxygen. There is some nitrogen in the thin air, but it is not a big, dense reservoir you can tap cheaply. Oxygen does not exist there in a free, breathable form. You have to make it, molecule by molecule, every liter, every breath. And that 100 square meter room, that one simple habitat, becomes a little chemical factory, constantly working just so the people inside can breathe and not have their blood boil. Maybe you're thinking, fine, we'll just scoop up the carbon dioxide that's already there, use it as raw material, and convert it to oxygen. Problem solved. We already tested that, right? NASA's MOXIE experiment on the Perseverance rover showed you can take Martian carbon dioxide and split it to make oxygen. So why is this still a problem? Because carbon dioxide itself is a headache, and scale changes everything. On Mars, at low temperatures and low pressures, carbon dioxide turns directly into dry ice, solid crystals that can clog filters, valves, and pipes. The atmosphere is full of fine dust, and that dust, combined with CO2 that freezes and thaws, is a constant stress test on every surface and moving part. CO2 can also react with water and some materials to form corrosive compounds over time, slowly attacking seals, metals, and plastics. Every intake system you build to pull in Mars air, every compressor that squeezes it, every line that carries it, is being hammered by temperature swings from maybe a few degrees above freezing down to minus 80 Celsius and beyond, plus dust, plus CO2 deposits. You're not just flipping on an oxygen machine and walking away, you're running a complex industrial plant in one of the harshest places you can find, and that plant must run 24 hours a day, every day, without long failures. Now, scale that up, not for one person, but for 10 people, 50 people, 100 people. Each human needs a steady flow of oxygen every second with no long interruptions. You can't miss a day because a valve jammed or a filter clogged. You need backup systems and backups for the backups. You need extra tanks already full of air, ready to keep the habitat alive while you shut down parts of the system for maintenance. All of that mass and complexity has to be launched from Earth or slowly built up on Mars over years. So when someone says, we'll just use the Martian atmosphere, that sounds simple, but the reality is you're in a constant engineering race against failure. You're fighting low pressure, the wrong gas mix, freezing temperatures, and corrosive behavior of CO2 just to achieve what Earth gives you for free the moment you're born, a lungful of air at the right pressure. And remember, everything we just talked about is only about air, just the invisible stuff you breathe. We haven't even touched the heat you need to keep that air warm enough, the energy needed to power all those compressors and reactors, the battle to stop that precious air from leaking out into the near vacuum outside. Because once you finally build that breathable bubble, you hit the next harsh fact about Mars. It is sitting inside a cold environment that is trying to suck the heat out of your habitat every second. And if you lose that fight, if your heaters fail or your power drops, all that carefully made air is still there, but now it is dropping toward freezing, then far below. Think about the coldest day you have ever felt on Earth. Maybe minus 20 Celsius, minus 4 Fahrenheit. Hard wind, your face hurts. Now understand this. On Mars, that kind of cold would actually count as a warm front. The planet's average surface temperature is around minus 60 degrees Celsius, about minus 76 Fahrenheit. That is the normal background, not a rare event, not a bad winter, just how the planet sits, day after day. And it is not stable cold, it swings hard. In many places, the temperature can jump or drop by tens of degrees in a single day. Near the equator, you might see the ground temperature creep a little above 0 Celsius, 32 Fahrenheit, for a short afternoon window. You might think, nice, it's around freezing, not that bad. Then the sun drops, and without a thick atmosphere to hold the heat, the surface radiates it away fast, and the temperature dives down again, maybe to minus 60 or minus 80 Celsius, minus 76 to minus 112 Fahrenheit. The reason is simple. Mars has almost no air and no oceans. On Earth, water and thick atmosphere act like a thermal blanket and a heat reservoir. They soak up heat when the sun is out and release it slowly when it's gone. That evens out day and night. Mars does not have that. Sunlight hits, the ground warms a bit, sunlight stops, the heat pours straight back into space. You are on a world that bleeds heat at every sunset and never really holds on to it. So if you want to live there, you don't just need a warm jacket. You need a controlled, heated pocket of air around you 24/7. That means habitats, suits, vehicles, all fighting that temperature drop all the time. The outside is not bad weather. It's an environment that pushes everything toward thermal failure. Inside your base, you want something close to human comfort, around 20 to 22 degrees Celsius, roughly 68 to 72 Fahrenheit. Meanwhile, outside might be sitting at minus 80 Celsius, minus 112 Fahrenheit, or worse. That's a temperature difference of around 100 degrees Celsius, around 180 degrees Fahrenheit, across maybe just a few centimeters of wall. If you imagine your habitat like a thermos bottle, it's a thermos someone drilled holes in and then dropped into a freezer. Every square meter of that outer surface is bleeding heat. Some goes out by conduction through the walls, some by radiation straight to the cold sky. There's almost no air, so convective heat loss is lower than on Earth, but it doesn't matter much. The radiation and conduction are enough. The larger your habitat gets, the more surface area you have, and the more total heat you lose, non-stop. Even a small cabin, let's say floor area around 50 square meters, about 540 square feet, with a dome or cylinder shape, can easily leak enough heat that you need several kilowatts of continuous power just to keep it warm. That's like running multiple space heaters at full blast, all day, every day, forever. Not for comfort, but just to stop the inside from drifting toward freezing, then below freezing, then towards the outside temperature. And you can't just accept it getting a little cooler sometimes, because if the interior drops too far, water in pipes starts to freeze, lubricants thicken, batteries lose performance, electronics drift out of their safe range. The cold doesn't just affect you, it attacks every system you depend on. So the heating is not optional, it's core life support, on the same level as air and water. You might think, okay, no problem. We'll cover Mars with solar panels. We'll capture sunlight and turn it into electricity. We already know how to do that on Earth, but the numbers flip against you as soon as you move out to Mars's orbit. At Earth's distance from the sun, the solar power hitting each square meter at the top of the atmosphere is about 1,360 watts. At Mars, that drops to around 590 watts per square meter, less than half. And that's before you even talk about dust in the air or dust coating the panels, or the angle of the sun at different times of year. After all those factors, the usable power per square meter can drop a lot more. So imagine you install a solar array rated for 10 kilowatts under perfect conditions. That might sound like a decent system, enough to run your lights, electronics, life support, heaters, and some extra gear. But on Mars, you're getting less than half the sunlight input by default. That 10 kilowatts might only give you 4 or 5 kilowatts on a clear day, and that's only when the sun is high and the panels are clean. At night, it's zero. During dust storms, it can drop toward almost nothing for days or weeks. To keep your habitat warm and your life support running, you now have to add huge battery banks or other storage to bridge the night and the bad weather. Batteries are heavy, fragile, and don't like extreme cold. You can add fuel cells, which means storing chemical fuels, or you can bring nuclear reactors, which handle the baseload power much better, but come with their own mass, safety, and engineering headaches. If you size your solar arrays optimistically based on a good day, and you misjudge the dust or the winter conditions, your margin vanishes. Your heaters cut back, the habitat starts cooling, the air circulation slows, the systems your life depends on drop into emergency mode. Cold on Mars is not just uncomfortable, it's the thing that exploits every tiny weakness in your power plan. Now, think about what happens if, instead of slightly underbuilding your system, something outright fails at the wrong time. On Earth, if the heater in your house dies on a cold night, it's bad, but you usually have time. You can put on extra clothes, light a fire, go to a neighbor, call a repair crew. The outside air is cold, but it's not instantly lethal. On Mars, if your main heating loop fails at sunset and you don't have enough backup, you are in a completely different situation. Inside your habitat, the air is warm at first. The walls are warm. The water tanks and furniture and equipment all hold some heat. But as soon as heating stops, all that stored heat starts flowing out through the walls into the far colder environment. Depending on how well you insulated the structure, the interior could drop below freezing in a few hours and then keep falling. You might go from shirt sleeves to heavy gear to emergency survival mode in a single night. As the temperature falls, parts of your life support system can start to fail one by one. Water and exposed pipes can freeze and expand, cracking the tubes, losing your water, and maybe flooding electronics when it thaws. Coolant in thermal loops can thicken. Pumps can stall. Batteries lose capacity in the cold. So even if you have power stored, they may not be able to deliver it at the rate you need. Valves and seals contract. Tiny gaps open. Air leaks increase, sensors start reading wrong or shutting down altogether. You get this chain reaction where one failure triggers another. A frozen line means no cooling for some equipment. That equipment overheats or shuts down, which then cuts power or airflow somewhere else. Now, oxygen generation is at risk, or CO2 scrubbing slows down, or circulation fans stop. The habitat is getting colder and the air is getting worse at the same time. All of this can happen while the outside is sitting at temperatures that will kill you if you try to spend too long out there fixing things in a suit. On Earth, when systems break, the environment is still fundamentally compatible with you. You can go outside while you figure it out. On Mars, the environment is actively helping your problems get worse. It is pulling heat out of your base. It is freezing your pipes. It is making your batteries weaker. It is pushing every piece of hardware toward its limit. And remember, all of this is just about temperature and power. Only the struggle to stay warm. Only the struggle to keep electricity flowing. We have not yet added the fact that above all of this, there's almost no magnetic field, almost no atmospheric protection, and the constant stream of radiation hitting your habitat and your body, even on the good days when everything else is working. Because once you step back and say, fine, we will pay the energy cost, we will fight the cold, we will bring reactors, you then slam straight into the next problem. Mars does not just freeze you, it slowly irradiates you every hour you spend on the surface. You know how we keep talking about air and temperature like they're the big killers on Mars? Here's the twist. Even if you solve both, even if your base is warm and full of breathable air, the planet is still quietly hitting you with something you cannot feel at all: radiation. All day, every day. On Earth, you're inside a shield you never see. Our planet has a hot, moving core, molten metal turning and churning. That motion generates a global magnetic field. This field reaches far out into space. It grabs a lot of the charged particles streaming from the sun, and it steers many of them away from the surface. Some get funneled down toward the poles. That is where you get auroras. The rest are bent around the planet or stopped high in the atmosphere by thick air that absorbs the energy before it reaches you. Mars used to have something like that. Early in its history, it probably had a stronger internal dynamo, but it cooled faster. The moving metal slowed down. The global magnetic field faded. Today, what's left are small, patchy regions of magnetized crust, localized spots that do not connect together into a real shield. They protect small areas a little bit, but globally, Mars is basically exposed. Charged particles from the sun and high-energy cosmic rays from deep space slam into its upper atmosphere and down toward the ground with much less deflection. So picture the situation. You're standing on a planet with thin air, almost no global magnetic field, and constant particle radiation coming in from above. You don't see it, you don't feel it, but your cells do. Your DNA does. Slowly, relentlessly. Let's put numbers on it. On Earth, at sea level, your average background radiation dose is around 2 to 3 millisieverts per year. That includes cosmic rays, natural radioactivity in the ground, even some from food. It is low. Your body's repair systems can usually handle it. On the surface of Mars, measurements from landers and orbiters suggest you're getting somewhere around 0.2 to 0.7 millisieverts per day, every day. That stacks up to maybe 70 to 250 millisieverts per year, depending on solar activity and local conditions. If those units mean nothing to you, think of it this way. On Mars, in 1 year, you might take 30 to 100 times the radiation dose you get on Earth's surface. In 2 or 3 years, you're in the same total range as a radiation worker's career limit. In that zone, the statistical risk of cancer goes up, the risk of cataracts goes up, stem cells can be damaged, and there is growing concern about long-term effects on the brain and nervous system. You're basically living in an environment that treats your whole body like it is sitting next to medical imaging equipment, except you never step out of the room. Now, you might say, fine, we'll just put some shielding over the base. We know how to block radiation, just add more material. That is true, shielding works, but it's not cheap or light. It's heavy, and on Mars, heavy means hard. A simple rule a lot of engineers use: if you want to cut down cosmic ray exposure by a meaningful amount, you want something like 5 to 10 grams of material between you and space. That can be water, special plastics, or rock and soil. All of those are basically mass. You can't cheat that. You have to move and stack it. Take a habitat with a roof area of 100 square meters, maybe about 1,000 square feet, a reasonable small base. If you decide to cover it with around 50 centimeters of Martian soil, about 20 inches, and if that soil's density is around 1,500 kilograms per cubic meter, you're looking at something like 75,000 kilograms of regolith on top, about 75 metric tons. That is not a thin dome. That is a heavy blanket of rock you have to dig up and move. Who moves all that? Either robots, which have to be designed, landed, powered, and maintained, or human crews in suits, doing hard labor in low gravity, under radiation, breathing tanked air, and limited by suit life and fatigue. That cute dome you see in concept art, bright and transparent, turns into a low, buried bunker as soon as you actually do the math. The planet's surface is simply too exposed to live under glass for long. You can try clever tricks like using water tanks as shielding or parking vehicles and storage modules around living areas, and those help, but if you want Earth-like safety over years or decades, you're still talking about significant thicknesses of material and serious construction just to make your living space not constantly hostile to your DNA. And all of this is just the baseline radiation, the steady drizzle. There's another layer on top, the spikes. Solar storms. Every so often, the sun throws a tantrum. Big eruptions called solar particle events or solar storms send bursts of high-energy protons and other particles streaming out into the solar system. On Earth, a lot of that energy is diverted by our magnetic field. Some of it hits the atmosphere and lights up the sky. Pretty auroras, extra radio noise, maybe some issues for satellites and power grids. On Mars, there is no big global shield to step in. When a large solar storm hits, the particle flux at the surface can jump, suddenly, by a lot. For an astronaut in a suit outside or in a lightly shielded vehicle or thin-walled habitat, a big event could push the radiation dose into the range of acute radiation sickness over hours. That means nausea, vomiting, drops in white blood cell counts, damage to bone marrow, and long-term increased cancer risk. A really bad event could be directly life-threatening. So now, on top of everything else, your colony needs dedicated storm shelters. Parts of the base with extra shielding, thick layers of regolith, water tanks, or heavy materials overhead and on the sides. You need monitoring systems watching the sun and space weather. You need procedures to get everyone inside those shelters fast when a warning comes in. You need to assume that people will be working outside when a storm hits and plan how they get back, how much dose they take, how many such events they can afford over a lifetime. And here's the ugly part. The warning systems and the shelters themselves are more machinery and more infrastructure that must not fail at the wrong time. If a detector goes down, if communications are cut, if a hatch sticks, the colony does not get a light show, it gets avoidable damage to human bodies. You might not see the effects for years, but they will be baked into the population. Higher cancer rates, vision problems, other health issues that never fully go away. So put it together. Mars is a world with almost no magnetic shield, thin air, constant background radiation much higher than Earth, and occasional storms that can push you into acute exposure if you are not protected. You can engineer your way around some of this with buried habitats, thick shielding, smart layouts, and careful operations, but you cannot turn Mars into Earth. The particles keep coming, the mass you need to block them stays huge, and the risk never fully disappears. And this is a pattern that keeps repeating again and again. You can fight the planet with technology, you can patch over one problem, air, then another, cold, then another, radiation. But none of these fixes are simple, none of them are truly permanent, and each one adds more systems that can fail. You might think, at least there's one thing Mars gives us, lower gravity. Walking is easier, lifting things is easier. Maybe that part is finally in our favor. But the truth is, that same low gravity that makes you feel light slowly breaks the body you evolved for Earth over months and years. It quietly rewrites your bones, muscles, blood flow, and even what it would mean to have children there at all. You probably think Mars's low gravity is the one part that feels like an upgrade, right? Less strain on your joints, easier to lift things, cool slow motion jumps. Here's the problem. Your body is not built for easy. It is built for 1G. And when you turn gravity down to 0.38G, the entire system starts quietly reprogramming itself in ways that are very hard to reverse. We already know what happens in 0G from the International Space Station. At 0G, astronauts lose bone density at something like 1 to 2% per month in key areas, especially hips and spine. Muscles shrink, especially in the legs and back because they are not holding you up anymore. Fluids shift toward the head. Faces puff up, legs get thinner. Vision can get worse because pressure inside the skull changes. The immune system can act weird. Wounds heal differently, hormones shift. It is a full body effect. And that's with extreme countermeasures. Astronauts on the ISS train about 2 hours a day, every day, with treadmills, resistance machines, cycling, all designed to simulate load. Even then, they come back weaker and need rehabilitation on Earth. That's from missions lasting months, not years. All of this happens at 0G, where your body has completely lost its usual reference. Mars is 0.38G, not 0, so it won't be as bad as orbit. But here's the big problem. We don't really know how bad it is over long periods. We don't have years of human data at 0.38G. We have short missions, models, and animal studies. That means if you move to Mars, you're signing up to be an experiment in human biology, with your skeleton, your muscles, your circulation, your brain, all part of the test. So what does that actually mean for your body when the load is not gone, just permanently turned down? Bone is not static. It's a living tissue. It responds to the forces you put on it. More load, more impact, and your body keeps bones thicker and stronger. Less load, and the system slowly trims away density it thinks you don't need. That's why bed rest or long hospital stays cause bones to weaken, not just muscles. At 0.38G, every step you take on Mars hits your bones with only about 1/3 the force of the same step on Earth. Your spine, hips, and legs are carrying a lighter you all the time. Over months and years, your body is likely to decide that thick Earth-grade bones are unnecessary. It will slowly adjust toward a new normal that works under Martian gravity, which probably means thinner, more fragile bones. Now imagine you spend 5 years on Mars, your whole body quietly recalibrating to that lower load. Then you try to come back to Earth. Suddenly, you're in 1G again. For your Mars-tuned skeleton, it's like someone instantly tripled your body weight. Every joint, every vertebra, every step is pushing way harder than your recent baseline. Simple activities, walking upstairs, carrying a box, even just standing up fast could be dangerous. Fragility fractures, breaks from relatively small impacts become a real risk. Your spine and hip bones, already thinner from years of 0.38G, now get pushed by full Earth gravity. You could end up in a situation where Mars colonists are technically able to ride a rocket home, but their bodies can't safely live on Earth without heavy medical support. Maybe exoskeletons, maybe long rehab, maybe never fully. And remember, this bone loss is happening at the same time as radiation damage. Radiation can weaken bone and harm bone-forming cells. So Mars is hitting your skeleton from 2 angles at once: lower gravity and higher radiation. This is not live light and have fun. This is slow-motion structural failure of your own body. But it is not just bones. Your fluids and your heart do not get to ignore the gravity change either. On Earth, gravity pulls blood and other fluids down into your legs. Your veins, your heart, your nervous system all adapt around that. Your blood vessels tighten or relax, your heart beats harder or softer to keep your brain supplied. In microgravity on the ISS, that pooling does not happen. Fluid drifts up toward the chest and head. Astronauts get puffy faces, skinny legs, some develop eye problems because the pressure in and around the eye changes shape. Their bodies adapt to a world where up and down do not matter. Mars gravity is in the middle. Not zero, not one. Some fluid will still pool in the lower body, but less than on Earth. That means your cardiovascular system might never fully load up the way it does here. Your heart does not have to work as hard against gravity. Your blood vessels may remodel to this easier condition. Over time, your whole system might settle into a weaker state, tuned for 0.38 G. Then again, you try to come home, or you just stand up quickly after lying down, your body, used to weaker demands, suddenly has to push blood upward in a 1G field. You can get dizziness, fainting, blood pressure crashes. The problems astronauts already face after a 6-month ISS mission when they try to stand on Earth again could become worse after years in partial gravity. And there's another twist. When you design artificial gravity systems like spinning centrifuges and habitat, you usually assume you're going from 0G to something close to 1G. You can set the spin and the radius to give your body a clear, consistent force. But on Mars, you're already at 0.38 G outside. That means if you build a centrifuge inside to boost people up toward 1G, you now have two different gravitational levels in the same daily routine. 0.38 G when you walk around the base, higher G when you train, back down again when you stop. It's unclear how well your body handles that switching long term, or what the ideal schedule is. You can't just guess, because guess wrong on Mars means real, permanent damage to people. All of this so far is about adults who volunteered for this life, people who signed the form and said, yes, I accept the risk. But what happens when you try to move from a research outpost to something real, a community, a place with children? If you ever try to have kids on Mars, you're making a biological bet with almost no data. Embryos, fetuses, infants, their whole development assumes 1G. Everything from how the inner ear forms to how bones grow to how the heart and lungs mature happens under Earth gravity. We have some animal studies in space, some gestation experiments in altered gravity, but nowhere near enough to say this is safe for human development at 0.38 G. Maybe some stages of pregnancy fail more often, maybe organ development is altered, maybe the brain's wiring changes in ways we don't like. Maybe it works, but the cost shows up later in joint problems, heart problems, balance issues. Or maybe the body adapts fine to Mars gravity, but becomes completely incompatible with Earth. A child born and raised on Mars might end up with bones and muscles and circulation tuned so tightly to 0.38 G that 1G feels like being crushed, like living every day in a suit of weights they cannot take off. At that point, you're not just moving people, you're creating a new population that may be physically locked to low-gravity worlds. A Mars-born human might never be able to walk normally on Earth, or might face serious medical risk trying. They would be, in practice, stranded, not by spacecraft technology, but by biology. Their homeworld would be a cold, irradiated desert they never chose, but their bones and heart would not give them any real alternative. And there's another ethical layer here that you cannot ignore. It's one thing for adults to choose that risk for themselves, fully informed. It's another to bring children into a place where the environment and gravity may permanently limit their options, not just for where they live, but for where they can ever go. You're not talking about explorers anymore. You're talking about a separate branch of humanity tuned to a hostile planet that cannot even support them without machines. So when people say, we'll adapt, humans are flexible, yes, we are. But adaptation here doesn't mean Mars becomes more like Earth. It means your body becomes less like an Earth body, weaker in some ways, more dependent, more fragile. It's adaptation that narrows your future, not expands it. And even while your skeleton is thinning, your blood is shifting, and your kids might be locked to 0.38 G, you still have to actually walk on the surface, suit up, go outside, and touch the ground. And that ground brings its own problem. It's not friendly soil, it's not beach sand, it's fine, sharp dust that gets into everything and may be toxic to you every time you breathe even a little bit of it in. You know what people always imagine when they hear Martian surface? Big rocks, red sand, maybe some pebbles under your boots, something that feels like a desert hike, hard but manageable. The reality is nastier. Mars is not covered in friendly sand. It is covered in extremely fine, sharp dust that acts like sandpaper and poison at the same time. This dust is not like the stuff on a beach. Beach sand grains are big, rounded by waves and wind. On Mars, most of the loose material is much smaller, often just a few micrometers across, smaller than the width of a human hair. And because there is almost no liquid water and almost no thick air to tumble and polish it, those dust grains stay sharp. Their edges do not wear down. So you're basically dealing with something closer to talcum powder mixed with microscopic glass shards. In the thin Martian atmosphere, this dust does not just sit on the ground. It gets lifted easily by the winds because the grains are so tiny and light. Once it's in the air, it stays suspended for a long time. It slips into gaps, sticks in crevices, finds every opening in your hardware. It'll work its way into suit joints, into seals, into air filters, into electronics housings. And if any of it gets inside your habitat or your suit, into your lungs, it's not just annoying, it's dangerous. Think about your spacesuit. Every time you go outside, you're walking through that dust. The joints around your shoulders, elbows, knees, hips, they all have moving parts, bearings, seals, materials that flex and rotate. If sharp particles get in there and grind around, they start chewing away at those parts like sandpaper. Over time, joints stiffen, seals weaken, the risk of a slow leak goes up. Now remember, on Mars, a slowly growing leak is not a maintenance issue, it's a life support issue. You might think, we'll just clean it off, brush it, wash it. The problem is, Mars also pushes this dust into a different mode, electrically. In low humidity with dry surfaces rubbing against each other constantly, materials charge up easily. Mars is extremely dry, and the dust grains rub against rocks, against each other, against your suit surfaces. They pick up static charge and then cling to anything they touch, like your visor, your solar panels, your radiators, your cameras. When NASA sent astronauts to the moon, they found lunar dust was so clingy it stuck to suits, scratched visors, and even caused coughing and irritation when it got into the lunar module. Mars dust will behave in a similar way, but your missions are not a few days, they're months or years. So your solar panels slowly get coated, their output drops day by day unless you constantly clean them. Your radiators, the devices that dump waste heat into space, can get a dust layer that changes how well they work. Your helmet visor gets smeared, making it harder to see, especially with sun glare. And all of this is happening while the same dust is trying to grind your suit to pieces from the outside. And we haven't even talked chemistry yet, because Mars adds another fun twist. The dust itself is not just mechanically bad, it's chemically unfriendly to your body. We know from landers and rovers that Martian soil contains perchlorates. These are chlorine and oxygen compounds, useful in rocket fuel, but toxic for humans. The concentrations measured are roughly 0.5 to 1% by weight in the regolith in some locations. That sounds small, but think about what that means in practice. Every handful of dust you track into the base, every smear you fail to fully clean off a suit, every tiny breach that lets dust float in, carries these chemicals with it. If perchlorate-laden dust becomes airborne inside your habitat and you breathe it, you're not just inhaling abrasive grains, you're taking in compounds that can interfere with your thyroid, damage tissues, and cause other health problems over time. If it gets on your skin or in your eyes repeatedly, you're asking for chronic irritation or worse. So now your air filters, your cleaning systems, your suit decontamination routines all have to be tuned not just to keep things tidy, but to keep a toxic dust from slowly poisoning your crew. What about farming? People love the idea of growing potatoes in Martian soil thanks to pop culture. In reality, if you just shovel that regolith into a greenhouse and plant crops, the perchlorates will go straight into that system. Plants don't like them, and you don't want them in your food or in the water cycling through your life support. So before Martian soil can be used for anything like agriculture, you have to wash it, flush it, bake it, chemically treat it, or you skip it entirely and go with hydroponics or aeroponics, growing plants in nutrient solutions or mist instead of dirt. All of those options mean more infrastructure, more water use, more power, more things that can break. Just to get to the point where your local soil is not actively hostile to the plants you're trying to grow, that's a long way from the romantic idea of digging a trench, planting seeds, and eating fresh vegetables under a glass dome. And we still have one more level to add. The dust doesn't just sit quietly. Now and then, it decides to go global. Mars is known for its planet-wide dust storms, events where dust is lifted high into the atmosphere, up to 50 or 60 kilometers, around 30 to 37 miles, across massive areas, sometimes the whole planet. During these storms, the sky can stay hazy for weeks or even months. The sunlight reaching the surface drops, in some places dramatically. Sensors on past missions have watched power output from solar panels drop as dust in the air thickened. This is not a quick one-day cloud. This is a long, dim period. For a colony that relies heavily on solar power, that's a direct threat. It's like living under a permanent smog layer that you can't predict exactly and can't clear. Your panels are already weaker than on Earth because Mars gets less sunlight to begin with, and now you're cutting that down further for extended periods. If you don't have big energy storage, or reactors, or other backup systems, your power budget shrinks while demand stays the same. You still have to heat the base, scrub the air, move water, run electronics. The dust storm doesn't pause your life support needs. The wind speeds in these storms are not like a hurricane on Earth. The air is too thin, so even at 30 to 60 meters per second, around 70 to 130 miles per hour, the actual force on structures is much lower. You're not going to see buildings ripped apart by pure wind, but you will see hardware get slowly buried, radiators blinded, and sensors blocked with dust. Landers we've sent there have watched dust creep up around them, cover deck surfaces, and sap their power until they shut down for good. So put this section together. You're on a planet where the ground layer is made of ultra-fine, sharp dust that slices into hardware, clings by static charge, carries toxic chemistry, and sometimes lifts into storms that dim your main energy source for weeks. To fight that, you need robust suits, advanced seals, constant cleaning systems, dust-resistant machinery, internal air handling that can trap and remove fine particles, soil processing plants, or complete avoidance of soil-based farming, plus a power system that survives long stretches of reduced sunlight. And remember, the dust is just one part of the surface itself. Even if you can keep it mostly outside, you still have to deal with the fact that the soil under it is not soil in the Earth sense. It's dead regolith, with almost no organic material, wrong nutrient balance, no natural life. If you want Mars to feed you, you're not starting with a rough version of farmland. You're starting with something that basically doesn't care whether life exists or not. So the next question is simple and brutal. If the stuff under your feet is not supporting life, not feeding plants, not cycling nutrients, what does it actually take to turn Martian ground into something you can grow food in at all? And what happens if that fragile artificial food system hiccups even once? When people say, we'll just grow food on Mars, it sounds like the easy part, right? You dig, you plant, you wait, you eat. But the ground on Mars is not soil the way you know it on Earth. It is not a living layer. It is basically dead ground, and that difference is huge. On Earth, topsoil is an ecosystem. It is full of organic carbon, dead leaves, roots, bits of animals. It is packed with bacteria, fungi, tiny insects, worms, all breaking things down, recycling nutrients, storing water, releasing it slowly. It's a self-tuning system that has been running for billions of years. You drop a seed into decent Earth soil, and most of the time the surrounding life helps it along. Martian soil is not soil. It is regolith, crushed rock and dust. It has almost no organic material, no built-in life, no natural recycling. The nutrient balance is off. There's basically no fixed nitrogen in forms plants can use. And you still have those perchlorates, the toxic chlorine-oxygen compounds riding along in the mix. If you literally went out, dug a trench, planted potatoes, and walked away, nothing good would happen. The plants would be starved, stressed by chemistry, and probably dead fast. So to grow anything there, you have to turn that regolith into something more like real soil, or skip it and go straight to high-tech farming. Either way, you just turned planting food into a chemistry and engineering problem. Plants are picky in a very specific way. They need macronutrients, nitrogen, phosphorus, potassium, the NPK you see on fertilizer bags, plus micronutrients like iron, magnesium, calcium, and others. They also need those nutrients in the right chemical forms and ratios. On Mars, the regolith does contain many elements, but they are often locked up. Phosphorus may be there, but trapped in minerals that dissolve slowly. Nitrogen is almost completely missing from the atmosphere, and the ground informs plants' like. Potassium and other elements might be present, but again, not in a ready-to-use state. So what do? You basically have two options. You import fertilizers from Earth, which costs a lot of mass and money and keeps you dependent on resupply, or you build a chemical industry on Mars. That industry would have to pull nitrogen out of the thin atmosphere, concentrate it, convert it into ammonia or nitrates, process waste products from your crew into usable forms, and mix all of that into either cleaned regolith or water-based growth systems. You're not just a colony, you're running a small fertilizer factory because the planet does not give you one. And even if you manage the nutrients on paper, there's the physical behavior of water in Martian ground to deal with. On Earth, pour water onto soil and most of the time it soaks in, spreads, and hangs around long enough for roots to use it. The air pressure and temperature range allow liquid water to exist for a long time. On Mars, the air is so thin and the temperature so low that liquid water at the surface is unstable. It tends to either freeze solid or boil away quickly. Inside Martian regolith, water can seep in and then freeze into ice, or it can evaporate into the tiny pore spaces and be lost. Getting a stable, wet root zone, a region where plant roots have a consistent mix of water and air, is hard. You're fighting physics and climate, not just garden design. That's why real plans for Martian farming usually involve sealed greenhouses with controlled pressure and temperature, or fully water-based systems like hydroponics and aeroponics, where roots sit in nutrient-rich water or mist inside a closed loop. But that moves the work. It does not remove it. Now, every kilogram of water in your farm is precious. You have to recycle almost all of it. You need pumps, filters, sterilizers, storage tanks, humidity control, all kept at the right temperature with the right chemistry. It is no longer a field. It is a machine that grows plants. You can get very high efficiency, but you pay for it with complexity. And this leads to the next big problem: food security. On Earth, your food supply comes from a huge area, millions of square kilometers of farmland, different climates, different crops. There are droughts, floods, pests, but if one region fails, others can still feed you. There is redundancy. On Mars, your entire food system might live in, say, a few hundred square meters of greenhouse, maybe the size of a small supermarket. And that's it. That volume contains most of the fresh food your colony can produce. Now, imagine what a single failure looks like in that setup. A leak in the greenhouse structure, and you lose pressure. Plants dry out or freeze, and you might have contamination in the life support loop. An airlock malfunction leaves a door stuck, preventing you from getting in to fix something at the critical moment. A pump fails, and water stops circulating to part of the system, killing a large fraction of the crop before you even notice. On Earth, a local crop failure is a bad season. On Mars, losing half your plant in your main greenhouse is a potential emergency that affects real people's calorie intake. You can stockpile dried food from Earth as a buffer, but that means more mass launched, more storage volume, and eventually resupply again. You might be able to write out one or two major failures, but your entire survival is tied to a small, fragile biological system that must work almost perfectly every week, every month, every year. And remember, the same dust and chemistry you're fighting outside are waiting to attack your farming systems too. Dust can coat greenhouse windows, cutting the light your plants get. Perchlorate contaminated regolith must be processed thoroughly, or you risk poisoning your crops and your crew. The thin air outside means any breach can flash water and heat out of your growing space far faster than you'd like, forcing you to have heavy structure, strong seals, and backup power just to keep the plants alive. So when people talk about living off the land on Mars, the phrase sounds comforting. It suggests local resources, resilience, independence. The reality is closer to running a delicate experiment on a timer. You're not tapping into a robust ecosystem. You're trying to build one from scratch inside a metal and plastic box on a planet that doesn't care if it fails. And all of that is before you even ask the most basic question about what those plants need: water. Because the water on Mars is not flowing in rivers or lakes you can pump from. It's frozen in the ground and locked in ice. And getting it into a form your crops and your crew can actually use is its own heavy, energy-hungry battle. You look at Mars and think, at least there's water, so that part's fine. But even that is a trap. The water is there, yes, but it's locked up in ways that turn every liter into an engineering project, not a simple resource. On Earth, if you want water, you drill a well, or you pump from a river, or you collect rain. It's already liquid, already moving, already part of a cycle. On Mars, most of the water is frozen, in the subsurface and in the polar caps. You're not tapping a river, you're mining ice. That means machines, not buckets. To get useful water, you first have to find the deposit, a layer of ice mixed with regolith at the right depth, close enough to your base that you can actually reach it. Then you drill or excavate, cut into that frozen ground, shovel it up, and move it to processing units. After that, you have to heat it, enough to melt the ice into liquid water, which costs energy, and then you have to filter out the dirt and dust mixed in. Even if the ice is not that deep, you're still spending serious power. Extracting 1 liter of liquid water, about 2 kilograms or 2.2 pounds, can easily cost kilowatt hours of energy, depending on temperature and depth. Multiply that by the hundreds or thousands of liters your base needs. Every day, your water supply is actually an ongoing mining and melting operation. If your heaters or drills go down, your water production drops immediately. And in some regions, especially where it is a bit warmer underground, the water you find is not clean ice at all. It is brine, salty liquid water full of dissolved salts, including those perchlorides again. That might sound convenient, liquid water, but chemically it is a problem. Those concentrated salts make the water unsafe to drink and unsafe for crops, at least without serious treatment. So now, on top of drilling and heating, you have desalination. You have to remove the salts, strip out the perchlorides and other contaminants, bring the water into a safe range for human bodies and plant roots. That means filters, ion exchange systems, reverse osmosis membranes, reactors, all the stuff you might see in a high-end water plant on Earth, but scaled down and shipped to Mars. Every extra piece of that chain is mass you had to launch, hardware you have to power, and another set of components that can clog, foul, or break. And remember, you are not doing all of this to get a couple of bottles per person. Your actual water demand, if you look at a full life support system, is huge. A human needs maybe 2 to 3 liters per day to drink, around half to 3/4 of a gallon. That is the bare minimum for survival. But your total water use is much bigger. You need water for hygiene, washing hands, minimal showers or sponge baths, cleaning equipment. You need water for growing food, whether that's in soil, hydroponic beds, or mist systems. You might also use water as part of oxygen generation, splitting it into hydrogen and oxygen in some systems. When you add all of that up, even with very conservative habits, your per-person water usage can easily move into tens of liters per day, and for more open, comfortable systems, it can push toward hundreds of liters per day per person. On the International Space Station, they recycle water aggressively. They reclaim moisture from breath and sweat and urine, and they still do not hit a perfect closed loop. Some fraction is always lost and has to be replaced from stored supplies launched from Earth. On Mars, any water you lose is gone permanently. There is no easy, we'll just schedule a delivery next week. Resupply missions are rare, months away, and cost a fortune in mass. So your recycling has to be better than what we run in low Earth orbit, more robust, more closed, with fewer losses, even though you are operating in a harsher environment, with more dust, more cold, more distance from help. Every leak, every spill that cannot be recovered, every pipe that blows out is a direct hit to your reserves. You can mine more ice, yes, but that assumes your mining and processing systems are up, your power is stable, and your crew has the time and spare parts to keep everything running. Water is not a simple stockpile. It's a constant flow that you have to keep pushing through a complicated loop. And that whole loop is fighting one enemy all the time: freezing. Outside your habitat, the average temperature is around -60 degrees Celsius, -76 Fahrenheit, much colder at night or in winter. Every meter of pipe that runs outside, every storage tank that touches the exterior environment, every filter or pump in an exposed area is at risk of freezing solid if heating or insulation is not perfect. On Earth, if a pipe freezes and bursts in winter, it's a mess. You mop up, call a plumber, complain. On Mars, if a pipe feeding your greenhouse freezes, that line can crack. You lose water into a place you cannot easily reach. The plants in that loop dry out or freeze, your food supply takes a hit. If a pipe in your main habitat bursts, now you have water spraying or leaking into electronics, shorting circuits, shutting down equipment that runs air handling, heating, or communication. Then that water freezes in the cold sections and expands, making the damage worse. To prevent this, you have to heat pipes, insulate them, route them inside controlled areas whenever possible. That means more power, more design constraints, more mass. It also means that every time you expand your base, every time you add a new greenhouse or lab, you're adding new risk points where freezing can happen if you miscalculate or if a heater fails. So water, which on Earth feels like the most basic, forgiving resource, becomes tight and fragile. You mine it with heavy machines, you melt it with hard-earned power, you purify it with complex equipment, you move it through lines that must never freeze or burst, you recycle it again and again, always watching for leaks, always watching your total reserves. That is not a blue planet feeling. That's a count every liter mindset. And all this time, while you're hauling ice, stripping salts, babying pipes, you're still living in a place where the air outside is nearly a vacuum, and your survival depends on pressure shells that must never fail. Because even if you somehow handled water perfectly, the structure you live in on Mars is not a normal building. It's a thin shell full of high-pressure gas sitting in a near-empty environment. And if that shell cracks, your carefully stored water and your carefully recycled air both rush out together. Think about the place you live right now. If a window cracks, if a tile falls off, if there's a gap under the door, it's annoying, but you keep breathing. The air outside is fine. The pressure outside is fine. Your house is just a box sitting in an environment that already supports you. On Mars, that's completely flipped. Your house is not a building. It's a pressure container holding back a deadly environment every second. Inside your habitat, you want something like 70 to 100 kilopascals of pressure, close to Earth's sea level. Outside, Mars gives you around 0.6 kilopascals, less than 1% of that. So every wall, every window, every joint is holding back a pressure difference of roughly 70 to 100 kilopascals. That is similar to what an airplane fuselage sees at cruising altitude. The difference is planes are pressurized for a few hours at a time. Your Mars habitat is pressurized nonstop, 24 hours a day, year after year. Structurally, that turns your home into a thin shell that is always under load. The walls want to bulge outward, joints want to flex, seals are squeezed and stressed. Every weld and bolt is part of the chain that keeps that pressure contained. Thermal cycles from hot sun to deep cold at night expand and contract the materials, tiny movements over and over. Dust works into gaps. Radiation slowly degrades some plastics and sealants. You're counting on engineering and manufacturing perfection to hold a life support bubble together in conditions that are constantly trying to pull it apart. So what happens if that shell is not perfect? What does small problem look like in a building that is pressurized in a near vacuum? On Earth, a 1 millimeter hole in your wall is nothing, maybe a draft, maybe a bug entry. On Mars, a 1 millimeter hole in your pressure hole is a leak path straight from inside to near vacuum. Gas rushes out because high pressure air always flows toward low pressure space. As the hole forms, the flow can start small, but as long as a pressure difference is there, it keeps going. Your air is literally escaping into the Martian environment. Sensors pick up the pressure drop. Alarms start. You now have a clock running. You have to locate the leak, get to it, and patch it, all before the pressure falls to a level where people start blacking out or your system shut down. And this is assuming the leak is small and stable. If the structure is cracked or a seal is damaged in a way that gets worse under stress, the leak rate can increase. You might end up in a situation where you cannot keep up, where even emergency pumps and extra tanks cannot maintain safe pressure. Then your only options are to evacuate to another sealed module, if one exists, or stay and watch your air bleed away. What can cause that tiny hole? A micrometeoroid, a small rock moving at high speed that punches into the hole. A manufacturing defect that went unnoticed, a bad weld that slowly grows into a crack. Stress corrosion from years of thermal cycling. A damaged seal in an airlock door that wasn't seated properly one day when people were tired. On Mars, any of those is not just a maintenance ticket, it's a potential life-threatening event. And remember, you won't have just one shell. You'll have connecting tunnels, airlocks, window frames, docking ports. Each interface is a place where materials meet and where leaks can start. The entire colony is a network of pressure vessels and seals that must all work together, most of the time with no major failures. Now, flip to the other big threat inside that same sealed bubble. Even if your walls hold perfectly, even if you never get a leak, you are still packing a lot of oxygen, plastic, wiring, and fabric into a closed volume and then running electricity through it. That's a perfect setup for the one thing space agencies fear almost as much as vacuum: fire. Inside your Mars habitat, the atmosphere is tightly controlled. Enough oxygen to breathe, maybe adjusted a bit to reduce fire risk, but still far richer than anything outside. You have cables, computers, pumps, fans, storage racks, clothes, packaging, all the normal human clutter. A small electrical short, a damaged cable, a faulty piece of equipment can give you a spark or a hotspot. On Earth, that might burn a corner of a room before sprinklers or firefighters stop it. On Mars, that fire is feeding on the same limited air your lungs need. In a sealed environment, a fire burns hot and fast. It consumes oxygen, generates heat, and releases toxic gases and smoke that spread quickly through the shared air. You can't just open a window to clear it. There's no outside breeze that will carry the smoke away. The outside is near vacuum and lethal. If you open something big enough to vent smoke, you're venting your breathable air at the same time. Fire suppression is also harder than it sounds. You can't just dump water on everything. Your electrical systems, your electronics, your life support hardware are everywhere. Water or foam inside racks full of hardware can turn one problem into many. Gas-based systems, like flooding a space with carbon dioxide or other suppressants, risk suffocating people along with the fire. You have to balance controlling the flames against keeping the atmosphere breathable, and you have to do it fast with limited people and tools. Every design choice inside the habitat becomes a fire question. What materials do you allow? How much plastic? What kind of insulation? What kind of fabric? How do you route cables? How do you separate high-power equipment from living spaces? Can you isolate sections of the air system quickly if smoke detectors trigger? Can you reroute airflow, keep clean air to one part while you let another part fill with suppressant? All of that has to be designed, built, tested, and then maintained correctly every year with no breaks. And that's just for a small crew module. Now imagine scaling up. People talk about Mars cities, tens of thousands of people, multiple domes, long tunnels, big shared facilities. It sounds impressive, but every bit of scaling adds more risk points, not fewer. The more people you have, the more volume you pressurize, the more modules you add, the more joints, seals, and interfaces you create. Each one is a potential leak, a point where a gasket can age, a bolt can loosen, a surface can crack. On Earth, we build huge, messy, imperfect cities. Buildings settle, pipes leak, windows warp, roofs crack. We tolerate a lot of small failures because the outside environment doesn't kill us. You patch things as you go, and if you miss a few, it's mostly an economic issue, not a survival issue. On Mars, that messy phase is deadly. A hairline crack in an airlock seal on a large habitat could leak enough air over hours to drop pressure below safe levels for dozens or hundreds of people. If a main corridor seal starts failing, you may have to seal off entire wings of your base, cutting people off from supplies and safe shelter. Every structure you add multiplies maintenance tasks, inspection tasks, and chance for human error. And as infrastructure ages, materials fatigue, radiation and dust take their toll. New construction gets added on top of old. If you're not extremely disciplined, your city becomes a patchwork of slightly different standards, repair histories, and weak points. The exact kind of messy sprawl that Earth's cities survive easily, but Mars cannot tolerate at all. The planet doesn't give you slack. It doesn't care that your maintenance cycle was behind that year. It will exploit every gap you leave. So when you picture a Martian settlement, stop imagining normal buildings. Think of fleets of spacecraft hulls, pressure tanks, and sealed tubes all bolted together, all under constant load, their skins holding back a 1-atmosphere pressure difference, their interiors full of flammable materials and electronics, and their survival depending on seals and welds that have to work day after day with human beings constantly walking in and out, carrying tools, bumping into things, making mistakes. You're not moving into a neighborhood, you're moving into a system that behaves more like a cluster of airplanes parked on a frozen desert, people living inside them full time, never allowed to step outside with a suit, never allowed to forget that one crack, one fire, one bad seal can turn the whole place from home into a death trap. And remember, everything this pressurized shell is protecting is not just people and furniture. It is an entire artificial Earth compressed into machines. Your air systems, your water systems, your waste recycling, your temperature control, your food production. Your real home is not the rocky planet under your feet. It is that tightly coupled life support network inside the walls. And if those systems start to fail in sequence, it is not a local problem. It is the whole environment inside turning against you. Here's the part almost everyone underestimates. On Mars, the real planet you live on is not Mars. It's the life support system you brought with you. Everything that Earth does automatically, with oceans, air, and ecosystems, you now have to do with machines, software, and checklists. And those machines do not get a day off. To stay alive, you need a stable supply of oxygen. You need carbon dioxide pulled out of the air before it builds up. You need humidity kept in a narrow band so your lungs do not dry out and your electronics do not corrode. You need temperature held in a tight range, not just for comfort, but so pipes do not freeze and equipment does not overheat. You need water recycled, waste processed, pathogens kept under control, and food produced at a steady rate. On Earth, all of that is happening around you right now for free. The atmosphere moves heat and moisture. Plants and microbes cycle carbon and nitrogen. Rivers and soils move and filter water. Ecosystems swallow up waste and break it down. You are sitting on top of a huge, self-correcting life support system that works even if you ignore it. On Mars, none of that exists. Every single one of those functions is an engineered loop. Air handling is fans, filters, pumps, valves, sensors, and software. Water recycling is tanks, membranes, heaters, and chillers. Waste processing is reactors and carefully tuned biology inside hardware. Food production is controlled lights, nutrient flows, and sealed growing spaces. You are basically carrying a small, fragile version of Earth inside a box, and if any major subsystem fails, the planet outside does not help. It just waits. Take just one piece of that loop, carbon dioxide. Every person exhales roughly 1 kilogram of CO2 per day, about 2.2 pounds. For a crew of 10, that is 10 kilograms every single day that has to be pulled out of the air before it builds up. In a sealed habitat, if you stop removing CO2, the concentration climbs, first to levels that give you headaches and fatigue, then to levels that cause dizziness, confusion, and eventually loss of consciousness. You're talking hours, not weeks. To prevent that, you need scrubbing systems running non-stop. Chemical scrubbers, like the lithium hydroxide canisters used on Apollo, directly bind CO2, but they get used up. You have to replace them. Regenerative systems, using materials like zeolites or special amines, can grab CO2 and then release it when you heat or depressurize them, letting you reuse the same beds again and again. That is what you want on Mars, because you cannot afford to ship tons of disposable scrubbers. But regenerative does not mean simple. Those systems have moving parts, heaters, valves that switch flows, seals that must not leak. They need regular maintenance, regular inspections, and they need backups. If one bed fails, another has to pick up the load. If a heater burns out, you need a spare. If a control valve sticks, someone has to suit up, pull the unit apart, and fix it. If for any reason the scrubbing performance drops faster than you expect, CO2 begins to rise, silently, until someone feels sick and checks the numbers. And remember, CO2 is just one gas in the mix. You still have to control oxygen levels. You cannot let them drop too low or rise too high. Too much oxygen makes fires more dangerous. Too little starves your tissues. All of this has to stay in a tight band while people are opening airlocks, moving between modules, exercising, growing plants, and running hardware that also interacts with the air. Now zoom out to the whole loop. We like to talk about closed-loop life support, water recycled, air recycled, wastes turned into fertilizer, plants feeding people and producing oxygen. It sounds clean and elegant. In practice, even on the International Space Station, it is still not fully closed. The ISS recovers most of its water from humidity and urine, but not 100%. Some is always lost. Oxygen comes mostly from splitting water with electrolysis, but the station still depends on regular resupply of tanks and spare parts from Earth. Mars doesn't give you that luxury. Resupply flights take months to arrive, and the launch windows only line up roughly every 26 months. You can't say, we're running a bit low on filters, we'll get more next week. You're trying to run a more complex life support system than the ISS, with more people, more agriculture, and more hardware in a harsher, dustier, colder environment, and you're doing it much farther from help. That means you need deeper redundancy, more spare parts, more on-site manufacturing capacity, better recycling, and more robust designs. And that, in turn, means more mass transported from Earth, more systems to maintain, more points where human mistake can break something. And this is where the most dangerous part comes in. Not the hardware, but the humans running it. On Earth, if a water treatment plant goes down, other cities can send bottled water, trucks can reroute, neighboring plants can pick up the slack. If a power station goes offline, other stations ramp up. The grid rebalances. Your lights might flicker, but the system is big and flexible enough to soak up a lot of mistakes. On Mars, if your main water recycler fails and the backup unit happens to be offline for maintenance, you're done. There is no third plant in the next town, no reservoir a few hundred kilometers away. Your water reserves start dropping. Maybe you have a few days or weeks of stored supply, but once that runs out, your only option is mining and melting more ice while you attempt repairs on complex equipment with limited tools under pressure. Human error makes this worse, not better. Someone misconfigures a valve, tries to isolate one part of the system, and accidentally cuts flow to another. Someone skips a maintenance step because they're tired and behind schedule. A filter that should have been replaced keeps running until it clogs. A gauge is misread, or an alarm is dismissed as a sensor glitch, and by the time someone realizes it's real, CO2 is already high, or water levels in a tank are already critically low. And failures rarely stay isolated. A problem in the power system forces you to shut down non-essential loads. Maybe you cut back lighting in the greenhouse. Plant growth slows. Your food reserve buffer shrinks. Later, a pump in the waste treatment line fails, so processed waste does not reach the fertilizer system on time. Crop yields fall more. Now you have an energy problem and a food problem, both tied back to a single early failure that seemed manageable. On Earth, those kinds of cascades get stopped by the sheer size and redundancy of our infrastructure. On Mars, your entire civilization might be a few connected modules and a couple of greenhouses. Every system depends on every other, in a tight feedback loop. So, when people say, we'll bring closed-loop life support and be fine, you have to unpack what that really means. It means building and running a machine that imitates the functions of an entire planet, with almost no slack, at the end of a supply chain that takes months to cross. It means betting your life that thousands of parts, software routines, and human procedures all work together correctly, over and over for years. And if that sounds fragile, that is because it is. The natural response you hear is, okay, so let's stop depending on machines so much. Let's fix Mars itself, make the air thicker, make the planet warmer, terraform it until it behaves more like Earth. It sounds bold, it sounds permanent, it sounds like the answer. But when you run the numbers on that dream, you find out that even turning Mars into a slightly less hostile version of itself is beyond anything we can actually do. There is not enough air to free, not enough warmth to trap, and not enough time for a human civilization to sit around and wait for a dead world to become a real home. You've probably heard the line, "We'll just terraform Mars," right? Warm it up, thicken the air, melt the ice caps, maybe even make oceans. Over time, it turns into a second Earth. We fix the planet instead of endlessly babysitting machines inside domes. It sounds bold and clean, the ultimate long-term solution. The problem is, once you actually run the numbers, that whole picture falls apart fast. The romantic version goes like this. You bombard Mars with greenhouse gases or giant mirrors. You warm the surface. That heat releases carbon dioxide frozen in the polar caps and locked in the ground. More CO2 in the air traps more heat, which releases more CO2. You get a runaway warming cycle. Ice melts, rivers form, lakes and maybe shallow seas appear. You seed the planet with hardy plants and microbes. They pump out oxygen, build soil, and over centuries, maybe millennia, Mars becomes blue and green. The sky thickens. You walk outside with just a jacket and an oxygen mask at first, then eventually no mask at all. It is a great movie pitch, but the planet does not care about our script. The hard limit is simple. There just isn't enough stuff on Mars to do what this story needs. Look at carbon dioxide first. Most terraforming ideas lean on it because Mars already has CO2 ice at the poles and CO2 locked into dust and rock. So people say, we'll just release it, melt the caps, heat the regolith, drive off the gas, and build a thicker atmosphere. But detailed studies of Mars's CO2 inventory point to a brutal conclusion. Even if you completely vaporized all known polar CO2 ice and drove out all the CO2 that's weakly bound in the dust and soil near the surface, you probably only get the surface pressure up to a few tens of millibars. For comparison, Earth's sea level pressure is a bit over 1,000 millibars. Mars today sits at around 6 to 7 millibars on average. So being generous, maybe you manage to push Mars up from a few millibars to, say, 20, maybe 50 in an optimistic scenario. That is still far below what humans need to breathe without pressure suits, and far below what liquid water likes if it's exposed to the open air. You do not get a thick, comfortable sky. You get a somewhat thicker, still thin CO2-heavy atmosphere, cold and unbreathable. And that's before you even ask how, in practice, you're going to vaporize polar caps the size of continents, or heat regolith over whole regions of a planet. That's mega engineering on a level we've never come close to. But even if you magically had that power, the payoff still falls short. You're spending absurd amounts of energy just to turn Mars into a place where you still can't walk outside without gear. Then there's the distance to the sun. Mars sits farther out, which means less incoming energy to work with from the start. On average, Mars gets about 43% of the sunlight Earth gets at the top of the atmosphere. That lower solar input locks in a colder baseline. To hold liquid water on the surface and keep large areas above freezing, you would need a very strong greenhouse effect, much stronger than Earth's. You're talking about pumping the air full of gases that trap heat extremely well and keeping them there. But once you talk about cranking up a planetary greenhouse that hard, you run into stability questions. How do you control it? What if you overshoot and trigger wild swings? How do you avoid making a dense, cold CO2 atmosphere where the pressure is higher but the temperatures are still miserable? On Earth, we worry about a relatively small change in greenhouse gas levels because it nudges climate in harmful ways. On Mars, you would be trying to force massive changes on a planet with no big oceans to smooth things out and no thick biosphere to buffer shocks. And underneath all that, the original problem we talked about earlier is still there. Mars doesn't have a strong global magnetic field. Even if you somehow built up a thicker atmosphere, the same solar wind that stripped it before would keep working on it, slowly eroding gas from the upper layers. You might get a denser atmosphere for a while, but keeping it for millions of years would be an ongoing fight. You're not just terraforming once, you're signing up to maintain a planet-sized life support project indefinitely. Then there's time. We like to think in terms of human lifetimes, maybe centuries on the optimistic side. Terraforming, if it's possible at all, is a project that runs on geological timescales, thousands to millions of years. You're talking about changing ice caps, carving river networks, building and stabilizing soils, evolving ecosystems that can survive Martian conditions and do useful work for you. That's not a 1 or 2 century problem. That's a deep time problem. Compare that to how our technology cycles actually work. We flip from one dominant system to another in decades, sometimes in less. Whole countries rise and fall in a few hundred years. Empires that looked permanent vanish, and their infrastructure rusts. You would be betting our species' survival on a continuous, coordinated engineering effort that has to last longer than any civilization we have ever built, through wars, collapses, resource swings, and social changes we cannot predict. There is also the ugly risk that you sink enormous resources into starting terraforming, and then the effort stalls. Maybe you raise the pressure and temperature a bit, but not enough. You end up in a halfway state where the environment is different, but still not good for humans. You have made Mars less like it is now, but not enough like Earth to help you, and you still need domes and suits, except now they have to deal with a more volatile climate on top of everything else. The key point is this. The idea that we will fix Mars until it feels like Earth is not a plan. It is a myth we tell to make the harsh reality feel softer. The real options in any reasonable time frame are much narrower. You can build small, sealed outposts, maybe a network of bases, maybe even underground or heavily shielded habitats. You can create pockets where humans survive with a lot of technology. But turning the entire planet into a place where you can walk outside, breathe normally, farm in open fields, and let kids play under an open sky, that is far beyond what the actual numbers allow. And even if you accept that, even if you say, fine, terraforming is a fantasy, we'll stick with domes and tunnels, you are still not done. Because outside those bubbles, the planet's climate is not calm. It is not a friendly background you can ignore. It is a thin, jumpy atmosphere that throws dust into the sky, swings temperatures hard, and can choke your power and visibility for weeks at a time. So if Mars is not going to be turned into a second Earth, if you are stuck inside sealed habitats forever, you need to understand the weather you're building those habitats in. Because on Mars, weather is not about getting wet or needing an umbrella. It's about storms and extremes that can quietly push your carefully balanced systems past a point where they hold. You'd think once you're inside a sealed base, weather stops mattering, right? The walls keep the Mars stuff out and you keep your own climate in. But that only works if what's outside is reasonably stable. Mars is not. The planet's climate is not gentle background noise. It is a set of fast swings and dust events that can quietly break your power, your hardware, and your plans. On Earth, a lot of chaos is smoothed out before it reaches you. Thick air moves heat around, big oceans store and release energy slowly, forests and vegetation interact with moisture and temperature. All of that acts like a buffer. It doesn't prevent storms, but it damps the extremes. Mars has none of those buffers. The atmosphere is thin, the oceans are gone, there's no global layer of plants to moderate anything. That means temperature swings are harsh. Local conditions can change quickly. One region can heat in the sun while another plummets into cold, and the thin air does a poor job of distributing that energy. Instead of a large, stable circulation pattern like we're used to, you get more abrupt changes, big gradients, and a climate that never really settles into something comfortable. Your base might see a quick drop or rise that stresses structures and systems, simply because the environment outside does not have the tools Earth has for smoothing things out. And when you add dust to that thin, jumpy atmosphere, things get even more unstable. Mars is known for its dust storms, and they are not just local gusts. The really concerning ones are the global events, the ones that can spread over most or all of the planet. These tend to show up around the time Mars is closest to the Sun in its orbit, perihelion, when the surface gets more solar energy. Dust on the ground gets lifted into the air, the sun heats that dust-laden air, it rises, that rising motion drives more wind, which picks up more dust, and now you're in a feedback loop. The more dust in the air, the more it absorbs sunlight high up, the more the temperature differences drive motion, which lifts more dust. This can grow from a regional storm into something that stretches around the globe. The surface under that haze sees less direct sunlight, the sky dims, and the usual day-night temperature pattern changes for weeks. For a crew living off solar panels, that dimming is not a minor detail. It means the power budget you planned for under clear sky conditions is suddenly wrong. Instead of getting, say, a few kilowatts from a 10-kilowatt array in normal Mars sunlight, you might see a fraction of that during a storm for days on end. If you didn't overbuild your power and storage for that scenario, your base is now draining batteries faster than you can charge them. You're forced into power-saving mode, cutting back non-critical systems, and hoping your estimate of storm duration was accurate. And even when the surface winds are not strong by Earth standards, they behave in a way that is specifically bad for your hardware. Surface wind speeds on Mars can hit 30 to 60 meters per second, roughly 70 to 130 miles per hour. On Earth, that's in the strong storm to hurricane range. But here's the catch. The air density on Mars is only 1% of Earth's. That means the actual mechanical force on large objects is much lower. You're not going to see big buildings knocked over simply from wind pressure alone. What you do see is dust lifted and carried efficiently. Fine particles get picked up, stay suspended, and then get dropped into every crevice they can find. It's not the wind shoving your structures around, it's the wind feeding a stream of abrasive, contaminating material into all the gaps. Over years, that is erosive. It sands surfaces, wears down coatings, and slowly attacks moving parts. Filters clog faster. Radiators lose efficiency as dust coats them. Hinges and seals pick up grit that grinds when they move. Solar panels get a layer that blocks light. Cameras and sensors get fouled. Every outside surface becomes a long-term maintenance item, not because it is being smashed, but because it is being infiltrated. To stay ahead of that, you need regular cleaning routines. Robots or crew out there brushing panels, blowing dust off radiators, inspecting exposed equipment. Every dust event adds more work, and missing a few cycles is not just cosmetic. It can directly reduce your power output and cooling capacity, which then hits life support and systems inside. Now, combine all of this with the fact that we do not fully understand Martian weather yet. We've had orbiters and landers collecting data for years, but that's nothing compared to the dense global monitoring network we have on Earth. We do not have an army of weather stations, buoys, and radar on Mars. We have a thin scattering of instruments and a lot of models that are still being tuned. On Earth, if a forecast is off, you might end up in traffic in a rainstorm, or your picnic gets ruined. Annoying, but survivable. On Mars, a bad forecast can be lethal. If you expect clear skies and plan a high-power activity, like a heavy drilling operation or a big greenhouse expansion, and instead you get a dust storm, your solar farm might not deliver what you counted on. Your batteries might not charge enough before night. Your heaters, pumps, fans, and scrubbers are now fighting over limited power. Or maybe you send a crew on a long surface EVA with rovers and suits planned around a certain temperature range and visibility, and the regional storm grows faster than expected. Wind speed goes up, dust thickens, visibility drops, navigation becomes harder. Solar charging on their vehicles collapses. Now you have people outside on a strict timeline with life support systems and vehicles that may not make it back if the environment cuts deeper into your margins than you planned. Your safety depends on models of an alien climate that we're still learning how to predict. If those models are wrong, or if data from orbiters is delayed, or if a sensor fails at the wrong time, your entire outpost can be caught underpowered, underprotected, and off guard. You can build in buffers, extra batteries, extra reactors, more conservative schedules, but all of that costs mass, complexity, and time. So when someone says, we'll just adapt to Mars weather, it misses a key fact. On Earth, adaptation is helped by the planet itself, by oceans, trees, and thick air that make the system somewhat forgiving. On Mars, the system is not forgiving. It is thin, jumpy, dusty, and poorly buffered. You are not adapting to a gentle background. You're trying to operate fragile, high-dependency machines in a place where the environment can swing hard while giving you much less warning and much less room for error. And even if you handle all that, even if your forecast is perfect, your power system is oversized, your cleaning robots are working, and your habitats hold steady, there is another layer you cannot ignore. It is not about what the climate does to your hardware, it is about what this whole setup does to you, to your mind. Because at the end of the day, you are still a human living in a metal can on a silent world, with the knowledge that outside those walls is a place you will never walk in shirt sleeves, never feel natural air, never be truly safe. That kind of isolation, at planetary scale, is its own threat, one that no amount of engineering can fully cancel. Here's the part people really don't like to think about. Even if you beat the air, the cold, the radiation, the dust, you still have to live there, mentally, day after day. Mars is not just physically hostile, it is psychologically extreme. You're not just far from home, you're on a different planet, and that distance is real in a way that hits your brain hard. Mars sits on average around 225 million kilometers from Earth, about 14 million miles. That number is so big it almost feels fake. But here's what it means for you. A radio signal, moving at the speed of light, takes anywhere from about 4 minutes to about 24 minutes to travel one way, depending on where the planets are in their orbits. So if you call home, you say hi, they hear it up to 24 minutes later, they answer, you hear that up to 24 minutes after that. There is no real-time conversation, no natural back and forth. Everything is delayed. Everything is one-sided for long stretches. If something goes wrong, you can't hop on a live call and get mission control to walk you through it second by second. You can send data and get advice, sure, but every exchange is slowed by that light speed lag. And rescue, that's not a thing in the way people imagine. No one is sending a quick emergency flight. The shortest trip with current propulsion takes months, and you only get good launch windows every 26 months or so. If your base has a serious problem, the only people who can fix it are already there. You and your crew are the first and last line of defense, always. Now mix that with the social setup. You're not living in a city of millions. You're in a small, isolated group, maybe 6 people, maybe 20. Studies from Antarctic winter stations, submarines, and space missions all showed the same thing. Small crews in confined, high-stress environments develop tensions, conflicts, mood issues. People get irritable, isolated. Some get depressed, some burn out. That's in places where you still have breathable air outside and evacuation is at least possible. On Mars, add a constant background fact in your head. A simple mistake here can kill everyone. Forget to close a valve, misset a pressure, misread a warning, and you do not just cause a bad day, you might damage air supply, water recycling, power. A small error can become a cascade of failures. And you know that. It is always there. You are living in a place where bad mood day and critical maintenance day can collide, and the cost of that collision is much higher than on Earth. Your neighbors are the same handful of people, over and over. You see the same faces at breakfast, in the lab, in the gym, in the airlock. You cannot go to another town. You cannot take a solo hike into real wilderness. You cannot meet new people unless a new mission arrives, which is rare. If you do not get along with someone, too bad. You still have to trust them with your life when they check your suit seals or run your air systems. And then there's the environment itself. You never really get to forget where you are because the planet does not let you. On Mars, you will never feel the wind on your bare face. You will never just step outside in a t-shirt and breathe. You will never walk through a forest, look up through leaves at the sky, or stand on a beach with waves hitting your feet. You will never swim in a natural lake or lie down in grass. Every single outside moment is in a suit, with a helmet, with a life support backpack humming behind you. You hear pumps and fans. You see through a visor. You talk through a radio. You are always aware of the gear, because the gear is what keeps you alive. Even nature on Mars is different. The landscape is beautiful in its own way, sure, but it is fixed in a narrow palette: rock, dust, ice, thin sky. There are no animals, no plants, no changing seasons filled with life. It is visually impressive, but biologically empty. We don't actually know what decades of that do to a human mind. Most of us are wired by evolution to respond to living environments, to variety, to the presence of other life forms. On Mars, outside the base, there is none. Inside, everything alive is controlled, cataloged, and fragile. Try to imagine raising kids in that, because that's what really living on Mars actually means. Not just research missions, but families, schools, culture, multiple generations. To have a real society, you need children. You need people who are born there, grow up there, go to classes, play, create art, argue, form friendships outside a mission structure. But Mars is a high-radiation, low-gravity, confined, high-risk environment. That makes having and raising children a massive ethical and logistical problem. We have almost no data on pregnancy and childhood development in 0.38 G under chronic elevated radiation, inside sealed habitats. You would be experimenting on humans in the most fundamental way. Parents on Mars would be making choices their kids never agreed to. Those children would not choose Mars. Mars would be chosen for them. They would grow up inside metal and plastic, with helmets as normal, with outside meaning suit checks and risk briefings. Their playground is a pressurized module. Their park is an artificial dome with controlled lighting and plastic grass. Their bones and hearts might adapt so strongly to Mars gravity that Earth becomes physically unreachable for them, not because rockets cannot carry them, but because their bodies cannot tolerate 1G without extreme medical support. You also have to think about education and culture under that pressure. Every lesson includes a subtext. If you mess this up when you're older, people might die. Kids are loud, they break things, they experiment, they test boundaries. They need some room to fail safely. On Mars, how much room is there for that? How many mistakes can you absorb when every system is connected, when air, water, power, and heat all live in a tight loop? You're trying to raise free, creative humans in an environment that punishes errors ruthlessly. And what happens when teenagers want to push back? When someone decides they are done with the rules for an hour, or they slip into apathy, or they decide they hate being trapped in a can on a frozen planet they never asked for. We barely manage mental health well in normal cities. How confident are we in doing it at the edge of survival, with no quick evacuation, no real escape, and a constant reminder that the entire world outside is trying to kill you? So yes, you can send trained, motivated adults for months or a few years. They can treat it as a mission, a sacrifice, a challenge, and many will handle it well enough. But calling that living on Mars in the same sense that we live on Earth hides the truth. You are not building a relaxed, open society. You're building a pressure cooker, socially and literally. And even while you're asking all of this from people, mentally and physically, you still have to feed them, supply them, give them medical care, provide tools, parts, and upgrades. None of that comes from Mars in the beginning. Almost all of it comes from Earth, down a supply chain that is longer, slower, and more fragile than any in human history. So the next question cuts to the core. If Mars is this hard on your body and your mind, how much harder does it get when you realize your entire civilization there is also permanently tied to rockets, launch windows, and factories on another planet, and there's no real way to cut that cord? Here's the brutal truth nobody likes to say out loud. A Mars civilization is not independent. It is a remote outpost at the end of the worst supply chain you can imagine. It never really unplugs from Earth, it just pretends to. Start with the timing. A resupply mission to Mars is not like sending a cargo ship across an ocean. You cannot launch whenever you want. The orbits have to line up. Good transfer windows open roughly every 26 months, a bit over 2 years. And even when you hit that window, the trip with current propulsion takes around 6 to 9 months one way. So from the moment someone on Mars says, "We're going to need more of this," to the moment that cargo actually arrives at their door, you're looking at something like a year and a half if everything goes perfectly. No delays, no launch failures, no problems on Earth. Imagine running a hospital or a power plant or even just a car repair shop where ordering a critical part means waiting 18 months. You cannot express ship anything. You have to predict what might break years in advance, build it into your cargo manifests, and hope your guesses are right. If you underestimate, you're stuck. If you overestimate, you ship heavy stuff you don't need and leave out something else you did need, because there's a second hard limit baked into all of this: mass. Right now, putting 1 kilogram, 2.2 pounds, into low Earth orbit costs thousands of dollars, depending on the rocket and the launch provider. Getting that same kilogram from Earth's surface to Mars orbit and then down through the Martian atmosphere to the ground costs more still, in fuel, in hardware, in mission complexity. Every kilogram in a Mars cargo bay is a fight. You are choosing between more medical gear or more spare parts, between extra food reserves or extra lab equipment, between building materials or more batteries. Your colony's hospital, your power systems, your spare suits, your life support hardware, your scientific tools, your mining rigs, all of them are fighting for space under a launch fairing every launch window. You will never have everything you want. You will have what you could pay to lift, what fit in volume and mass limits, and what someone decided was a priority 2 years ago. You will run short of weird, random things: seals in a certain size, a specific connector, a calibration tool, a medicine you didn't think you would need that much of. So people say, fine, we will make more things locally. We will use local resources, build a Mars industry. That idea is right in the long term, but you have to be honest with what that really looks like. To be even partly independent, a Mars settlement needs its own mining operations, pulling metals from the ground. It needs refining, turning ore into usable metals. It needs manufacturing lines that can build pressure holes, structural beams, piping, fasteners, circuit boards, cables, batteries, medical devices, vehicles, tools. That is not a small machine shop on the edge of town. That is an entire industrial base transplanted to another planet. On Earth, our ability to fix things depends on millions of workers and thousands of factories spread over many countries. You want a pump, a motor, a chip, a valve. It came from a complex global chain. On Mars, you might have a few hundred or a few thousand people at best trying to recreate enough of that capability to keep their own life support and infrastructure going. They will be very good, very resourceful, but they're still playing industrial catch-up in a place where every mistake is dangerous. Until that full stack exists, every broken circuit board, every failed pump, every cracked visor is potentially a single point of failure. If you do not have a spare and you cannot fabricate a reliable replacement locally, you are stuck waiting for the next launch window. Or you are cannibalizing other systems, ripping parts from one function to keep another alive. That might keep you going in a crisis, but it makes the whole system more brittle in the long run. And while all of this is happening, you are accumulating people, infrastructure, and risk. Because the dream is not just a tiny research station. People talk about cities on Mars, hundreds, thousands, maybe more living there. The problem is a city in that environment behaves very differently from a city on Earth when something goes wrong. Here, if a region is hit by disaster, people evacuate. Cars, Buses, trains, planes, ships, they move millions of people out of danger zones. They go to neighboring towns, other states, other countries. It is messy, but it is possible. We have seen it. On Mars, evacuation on that scale simply does not exist. The number of seats on spacecraft sitting ready at any time will be tiny compared to the number of people on the ground. Launch windows are rare, and each launch needs fuel, maintenance, and preparation. If a major failure hits a Mars settlement, something that poisons the main water supply, or damages key life support hardware across multiple modules, or creates structural problems with radiation shielding, you can't just decide to move everyone to safety. At best, you might have enough capacity to send a small fraction of the population back to orbit over multiple trips, probably over months, if the landing site and launch vehicles themselves are not damaged. Everyone else is stuck riding out the situation with whatever resources they already have. So, a city on Mars is not like a city on Earth. It's more like multiple remote oil rigs or Antarctic stations fused together, but without lifeboats big enough for everyone. It's a place where if something truly large goes wrong, the whole population is committed to solving it on site, with no realistic option to just leave. The margin for screw-ups shrinks again. Put all of this together and you get the real picture. Physically, Mars is harsh. Psychologically, Mars is harsh. Logistically, Mars keeps you on a permanent leash to Earth. Your food systems, your medicine, your replacement hardware, your new tools and upgrades, your emergency supplies, all point back to factories and launch pads on another world, far away. So when people say Mars will be our backup planet, they skip a key question. Backup for who? For a small number of highly trained people who are totally dependent on a fragile chain of rockets and shipments and who can never walk away from their machines without dying? That is not a backup civilization. That is a risky, expensive outpost. And that sets up the final question we have to face honestly. If surviving on Mars means living inside pressure cans, tethered to machines and supply ships, with bodies wearing down in low gravity and minds under constant stress, is that really living in the same sense we mean when we talk about living on Earth? Or is it something much narrower, survival on the edge, that we're trying to sell as a new beginning? So after everything you've heard, here's the real question. When people say we can live on Mars, what are they actually talking about? Are they talking about normal life, the way you live on Earth, or something much narrower and much harsher? If your bar is this, a few hundred highly trained people, carefully selected, heavily monitored, living inside metal cans can survive on Mars as long as the gear mostly works and Earth keeps sending ships, then yes, that is probably possible. That is not a civilization. That is an extended expedition. It's like a permanent research station with no easy way home. You are camping at the edge of death and calling it a neighborhood. You could keep that going for a while. You rotate crews, you send replacement parts, you upgrade systems over time. You run experiments, explore, dig, drill, map. That is good science, good engineering, maybe even good practice for deeper missions. But it is not the same as saying Mars is a place humans can live. Because as soon as you make that leap, you are talking about something else. Families, random people, people who are not engineers or astronauts, people who will make dumb mistakes on bad days, the way we all do here. On Earth, the planet absorbs a lot of those mistakes. Crops fail in one country, another country exports grain. A hurricane hits one coast, other regions send food, equipment, rescue teams. You forget to close a window, your room gets cold. Not lethal. A treatment plant messes up, bottled water can be trucked in from somewhere else. There is slack in the system, not because we are perfect, but because ecosystems and huge networks of people and infrastructure spread the risk out. Mars gives you none of that slack. Every system you build is a single point of failure for the people who depend on it. Your air system, your water recycler, your power plant, your greenhouses, your radiation shielding. Your body does not have backup air outside the hull. If the scrubbers fail and the backup is down, CO2 climbs and there's nowhere else to go. If your main greenhouse gets hit by a leak or infection, you can't just import truckloads of food from the next valley. There is no next valley with farms. Every human on Mars needs a functioning suit to go outside, a functioning habitat to sleep in, functioning pumps, heaters, filters, and software for every breath they take. Every birth, every illness, every accident plugs into that same fragile stack. There's no outside help in the normal sense. There's only whatever you already brought and whatever you can build right where you are. And underneath that, you have the things you cannot negotiate with at all: biology, physics, and time. The low gravity slowly rewrites your body. Bones thin, muscles weaken, circulation changes. The radiation slowly stacks up damage in your DNA and your cells. The dust works into seals and lungs. The cold keeps attacking every pipe and tank. The climate keeps throwing dust storms and temperature swings at your hardware. None of those are bugs you can patch. They are direct consequences of the planet's basic properties: Mars's mass, its distance from the sun, its lack of a strong magnetic field, its thin atmosphere. Those are fixed. We can engineer around them for a while, but we cannot change them. You can add more shielding, more exercise equipment, better medicine, heavier suits, smarter filters. You absolutely can reduce the risk and stretch out how long people can stay. But there is always a cost: more mass to launch, more systems to maintain, more failure modes. The longer you push the outpost to act like a normal place, the more you stack complex machinery against simple physics. And physics always gets the last word. That does not mean Mars is useless. Far from it. Mars is an amazing laboratory. It tells you how rocky planets evolve, how atmospheres are lost, maybe how often life starts or fails to start. It is a natural test site for robots, habitats, drills, nuclear reactors, life support systems. It is a place where short or medium-term human missions could do incredible science and push technology forward. You can absolutely imagine crews staying for months or a few years, rotating in and out the way we use Antarctic stations or the ISS, just much further and harder. But calling that setup a place humans can truly live in the same way we mean it when we talk about living on Earth is a category error. It is like pointing at a submarine and calling it a seaside town. Yes, there are people inside. Yes, they can stay there for a long time. Yes, they can work, eat, sleep, joke, and send messages home, but they are not living freely in that environment. They are surviving in a machine that keeps the environment out. That is what a Mars base is at its core: a cluster of submarines and spacecraft glued to rock. Everything human about it, every bit of warmth, air, water, food, light, and sound is coming from hardware, not the planet itself. You're not moving into Mars, you're parking on Mars and turning your back to it, because the outside world is something your body cannot tolerate for more than a few minutes without full protective gear. So when you hear Mars is our second home, you should now be able to mentally translate that. What it really means is we might be able to keep a small number of people alive there with a lot of effort, a lot of risk, and a permanent lifeline back to Earth. That is impressive, difficult, and maybe worth doing for science and for learning, but it is not a backup Earth. It is not an escape hatch for billions, and it is not a place where humans, as a species, can relax and actually live the way we understand that word right now. Mars is a laboratory, a proving ground, a harsh training area for deep space operations. It is a place we should explore, carefully, and maybe visit in person. It is not, and in any human time frame will not be, a true home in the way this planet is. Here, you can walk outside and forget that you are riding a rock in space. There, you will never forget, because if you do, Mars will remind you, fast. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. If you enjoyed the video, consider subscribing to the channel and like the video.